Hey, fellow problem solvers, Colfax Math here. Just watching me juggle isn't going to teach you how to juggle. The way you learn how to juggle is you got to practice. And that's the exact same thing with math. You can watch me derive this, figure out some of this, but you got to do a lot of practice problems. So you should have a notebook out in front of you, taking notes, and then a lot of practice problems to really solidify the idea. This video is going to be the derivation of the double angle identity in Trig Identities. It is from this book right here, Math SL AA, and it's in chapter 12. So what we're doing today is we're going to derive the double angle identity, and there are four of them. They're right here. Sine of 2 theta is equal to 2 sine of theta cosine theta. There's only one for the double angle for sine, but 3 for cosine of 2 theta. Cosine of 2 theta is equal to 1 minus 2 sine squared of theta, or it could be equal to 2 cosine squared of theta minus 1, or it could be equal to cosine squared minus sine squared of theta. Whenever you see any of these, you should be thinking Pythagorean theorem. So that's going to be part of the substitutions we do here. Okay, so let's go ahead and get started. Everything here in trigonometry starts by drawing our unit circle. It is called our unit circle because the radius on it is 1 unit long. I could rotate angle theta up, and I could rotate the same amount down to give me another theta here. So whatever angle that is, that one's the exact same. This is also a radius inside that circle, and then I'm going to label some of the points. So let me change colors here. I'm going to call this point A, this point B at my origin, this point C, and then I'm going to draw this line right here, and this is going to be line AC. So I can see that line segment AC is going to be equal to this plus this. Well, I know that sine of theta is equal to opposite over hypotenuse, but I could see that the opposite, because the hypotenuse is 1, is going to be sine of theta. So line segment AC will be sine of theta plus sine of theta. So I have one sine of theta plus another sine of theta. So AC is equal to 2 sine of theta. Okay, now I'm going to use the law of cosines. We're really going to use all of the pieces we've learned so far, not only in this class, but really for years of high school math. So using the law of cosines is this squared is equal to this squared plus this squared minus 2 times this cosine of that. So our law of cosines is a squared is equal to b squared plus c squared. Really a Pythagorean theorem. Taking into account it's non-right. So minus 2 bc cosine of the angle opposite that. So I'm using the law of cosines on this red triangle here. So I'm going to say this right here, AC squared. AC squared is equal to this leg squared, 1 squared, plus 1 squared, minus 2 times 1 cosine of this angle. Well, that angle is 1 theta plus another theta, or 2 theta. That's where the double angle is going to come in. And I also know that AC is equal to 2 sine of theta. So I'm going to take that and substitute it in right there. So that means I have 2 sine of theta, quantity squared, is equal to 1 squared plus 1 squared minus 2 times 1 cosine of 2 theta. And then right here, 1 plus 1, that's equal to 2. So I have 2. Let me go ahead and square this. 2 squared is 4. Sine squared is sine squared of theta. And that's equal to 2 minus 2 cosine of 2 theta. Divide both sides of the equation by 2. 4 divided by 2 will give me 2 sine squared of theta is equal 2 divided by 2, 1, 2 divided by 2 minus cosine of 2 theta. Clean that up a little bit. Let me add this to this side to get cosine of 2 theta is equal, right, it's going to be positive on that side, that 1 right there, minus 2 sine squared of theta. Just go back a page, and we have cosine of 2 theta is equal to 1 minus 2 sine squared of theta. Everybody good to go there? It's a lot. So there's the derivation of the first double angle identity. Now with all that said, let me write up my Pythagorean identity here. Cosine squared of theta plus sine squared of theta is equal to 1. Pythagorean identity. I have a sine squared here, so I'm going to try and get this sine squared by itself by subtracting cosine squared from both sides. So I'm going to subtract cosine squared from both sides to get sine squared of theta is equal to 1 minus, I'm subtracting that, cosine squared of theta. Again, here's my double angle identity. That's the derivation of it. And now I'm just going to derive another version of the double angle identity using the Pythagorean theorem. So let me erase everything above here so I stay on the same page. Let me erase this. And then take this value of sine squared of theta and plug it in right there. So I have cosine of 2 theta is equal to 1 minus 2 sine squared of theta, but sine squared of theta is 1 minus cosine squared of theta. So I'm going to replace this sine squared right there with this. 1 minus cosine squared of theta. I'm going to distribute that negative 2 through the quantity. So I have cosine of 2 theta is equal to 1 minus 2 minus minus plus 2 cosine squared of theta. Just clean this up a little bit. 1 minus 2 is negative 1. So I have cosine of 2 theta is equal to this, 2 cosine squared of theta, 1 minus 2, minus 1. So there's a second double angle identity. Just go back to our page of them. Cosine of 2 theta is 2 cosine squared of theta minus 1. So that's how I derive 2 of them. I really like those derivations so you see where they come from. Pretty much on any math test, you'll have a reference sheet with these double angle identities on there, but they're not made up. They're derived. And an identity that is something that will hold true in all cases. So if theta were a 1 and I plugged it in, it would work here. Or if theta were 1 million and I plugged it in for theta, it would work. It would work in all cases. So here are our 4 double angle identities. And I know there's a lot here. If you have any questions, please post them in the comments. I appreciate you watching. Thank you.